There we go. Okay. Sorry, guys. I joined the wrong Zoom meeting at first there. So today's a big day for us. Crack your knuckles, stretch your back. Today we are starting to talk about infinite series, which is an enormous topic and frankly a very challenging one. So today we are going to get the definition of an infinite series. We're going to get the definition of convergence of an infinite series. And you're going to get your first two convergence tests for infinite series. One is called the test for divergence, and the other one is a theorem on geometric series. Make no mistake, this shit is hard. There's a lot of notation. And so I just want to jump in and get going because we got a lot to do. One of the challenges here is the notation. It's called sigma or summation notation, the notation for sums and series. This is the Greek letter sigma, capital Greek sigma, and it stands for the word sum. So if you see something like this, this is a shorthand for an addition problem. The way you read this is you're going to add up or sum this thing as n goes from here to here. It's similar to an integral, only because the inputs are discrete whole numbers, there's finitely many of them, you can actually do it by hand. No crazy calculus required. So this says take 1 over n, add it up as n goes from 1 to 5. All right, that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. Is anybody seeing this for the first time? You all got through Calc 1 and you all took pre-calc, but I know that different strokes for different folks. Some professors are allergic to challenging things. So give me a thumbs up if you have seen sigma summation notation. Dope. All right. Pretty much everybody. So if your pre-calc and Calc 1 classes managed to both avoid this, that's first alarming because that means you didn't talk about Riemann sums. You may want to just spend a minute reviewing the summation notation, just reviewing what this sigma means. In general, if an is a sequence, if you have a sequence an, you can form a sum out of the terms of an. So like here, an would be 1 over n. And in general, I could look at the sum from maybe 0 up to wherever you wanted, like 4 of an, and that would be a0 plus a1 plus a2 plus a3 plus a4. Today, what we're going to try to do is figure out what happens when this shit goes on and on and on forever. So what about sums that go on forever? That would be something like maybe the sum from 1 to infinity of 1/2 to the n. I could start writing this out kind of with the same intuitive idea of the summation notation. This says add up all these powers of 1/2 as the power n goes from 1 all the way to infinity. So this would be like 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3, plus 1/2 to the 4, plus 1/2 to the 5, plus 1/2 to the 6, 1/2 to the 7, 1/2 to the 8, on and on and on, forever. There's a handful of challenges here. Of course, the first being that if I try to write this out, the sum that goes on and on and on forever, my hand will fall off before I finish. I will die before I finish. The world and the universe will cease to exist before I finish because the sum goes on forever. It would take me forever to write. So we're not going to get there by writing out the whole infinite series. That's impossible. When faced with challenges like these, mathematicians do a few things. We like to look for patterns, and we like to find analogies between the thing we're trying to fuck with and the things that we've fucked with in the past that remind us of that. This reminds me of an improper integral, the integral from 1 to infinity of 1/2 to the x. And remember, the way we handle that stuff is by writing it as a limit r to infinity integral 1 to r 1/2 to the x. So if I wanted to do the integral from 1 to infinity, I first do the integral from 1 to r, and then I take the limit as r goes to infinity. We do the same thing for infinite series. So maybe we should define the sum from n equals 1 to infinity of 1/2 to the n to be the limit. I'll use capital N for my symbol here, limit as capital N goes to infinity of the sum from 1 to capital N of 1/2 to the little n. And indeed, that turns out to be the way to do it. Very much analogous to your improper integral, where the integral from 1 to infinity is done as the limit r to infinity, integral 1 to r. Here, the sum from 1 to infinity will be done as lim capital N to infinity, sum from 1 to capital N. The analogy is very, very strong. So strong, in fact, that I'll be showing you a theorem on Wednesday describing the precise connection between these two things. Or in general, and here comes the definition of an infinite series. If I have an infinite series, I'm going to call it S, is the sum from n equals 1 or 2 or 0 or wherever. I'll say from 0 to infinity of an. We define it as sum n from 0 to infinity of an is the limit as capital N goes to infinity, sum n from 0 or wherever to capital N of an. There's some special names. We call the sum from wherever up to n of a sub little n, we call that thing S sub capital N, the nth partial sum.
After we're finished with the definition, can we have a few seconds to write it down real quick?
Sure. So I'm going to push this up a little bit because we do have to move somewhat quickly today. There is a lot to cover. Just like with improper integrals, the main question is this thing finite or infinite? With infinite series, the main question is this thing finite or infinite? And corresponding to that, we have the word converge. You know, the result is finite, or if the result is infinite, or if for whatever reason doesn't exist, we call that divergent. So we say the series S equals sigma little n from wherever, I'll say 1 to infinity, could be 0 to infinity of an, converges if the limit as capital N goes to infinity of the sum from 1 or wherever to capital N of an exists and is finite, i.e., the sequence of partial sums converges, right? Because this thing right here is the partial sum, Sn. I'm going to try to show you something that will give you a little bit of intuition for this. So remember, S, the full infinite sum here should be A1 plus A2 plus A3 plus A4 plus A5, all the way out forever and ever, amen. S1 is just A1. S2 is A1 plus A2. S3 is A1 plus A2 plus A3. I'm going to push this up now. S4 would be A1 plus A2 plus A3 plus A4. And in general, Sn is A1 plus A2 plus A3 out to wherever An. And you can write this more compactly as the sum from 1 to capital N of An. So let's think about it. If this whole infinite series that goes on and on and on forever can be made sense of, I should think of it as the limit of these things. All right, this is the series of length infinity. This is the series of length 1. This is the series of length 2. This is the series of length 3. This is the series of length 4. If S exists, it should be the limit of the series of length n, because S is the series of length infinity and Sn is the series of length n. And this is exactly what we had written on the previous page, that the full infinite sum, the sum from 1 or wherever to infinity, is the limit as n goes to infinity of the finite sums. And it's just the name, the finite sum is called Sn.
Is the first one S prime?
No,
Or-
it's here. No, I just used the bar on my S to make it obvious
Oh,
it's a
okay.
capital. Yeah.
Thank you.
So I want to return now to that very first example we had and see if we can't start wrapping our heads around it. I'll give you a second to write, but again, we do need to be moving somewhat quickly here today because there is a lot to get through. A warning, a little note. Sn is not the same as An, right? Sn, like S3, is not just A3, it's A1 plus A2 plus A3. Sn is the nth partial sum. It's the sum of the first n terms of the series. All right. So let's use the definition to investigate the convergence of the series S equals sigma n from 0 to infinity 1/2 to the n. Here my series is starting at n equals 0 and going up to infinity. So this would be 1/2 to the 0 plus 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3, and so on forever and ever. That's 1 plus 1/2 plus 1/4 plus 1/8, and so on forever and ever. And of course, this big ass addition problem goes on forever. I can't just solve it. So I need to use the definition that we just wrote down to start trying to wrap my head around it. We know, according to the definition, that S is the limit as capital N goes to infinity of Sn. All right, that's what we just wrote down. Well, what is S0? S0, that's A0, that's 1/2 to the 0. S1 is A0 plus A1, that's 1/2 to the 0 plus 1/2 to the 1. So 1/2 to the 0, that's 1. 1/2 to the 1 is 1/2, so this is 1 plus 1/2. I'm going to pull up a calculator here so we can play some games with decimals. I would like to refresh this if I could. Yeah, clear all. So 1 is 1, 1 plus 1/2, that's 1.5. The next partial sum, S2, that's 1/2 to the 0 plus 1/2 to the 1 plus 1/2 to the 2. That's 1 plus 1/2 plus 1/4. So I'll start typing these in. This is 1.75. The next partial sum, S3, is 1/2 to the 0 plus 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3, or 1 plus 1/2 plus 1/4 plus 1/8. So again, I'll come back to my calculator. Oh, shit. 1 plus 1/2 plus 1/4 plus 1/8. This is 1.875. Let's do another few. So S4, I'm going to skip writing it like this and just write it like this. That's going to be 1 plus 1/2 plus 1/4 plus 1/8 plus the next term is 1/2 to the 4, or 1/16.
Does it converge onto 2?
Let's see. So this guy is 1.93, 1.9375. And yeah, if we keep going here, these partial sums, Sn, appear to be getting closer and closer to 2. We'll write this last one out. This is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 would be the next term. And yeah, 1.968. So remember, the full infinite series S is the limit of the SNs. And here we've calculated the first few SNs. It appears that the limit as n goes to infinity of the SNs is 2. So we would say that the series S equals sigma n from 0 to infinity of 1/2 to the n converges to 2. Converges because the sequence of partial sums appears to have a finite limit. The sequence of partial sums appears to be a convergent sequence. And since when the sum gets longer and longer and longer, the partial sums get closer and closer and closer to 2, the full infinite series, we say, has value 2. There is a way to interpret this particular one geometrically. If I start with a rectangle where this side length is 1 and this side length is 2, and I start chopping it up, then this piece has side length 1. I divide each one by half, so this area here is 1. And then I take this guy and I chop him up. This has area 1/2. Then I chop this guy up. This has area 1/4. And then I chop this guy up. This has area 1/8. And then I chop this guy up. This has area 1/16. And if I continue this pattern of chopping and chopping and chopping, there's 2 ways to interpret the area. On the one hand, the area is 2 times 1, which is 2. On the other hand, the area is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. That's my infinite series right here. So if you let this pattern continue on and on and on forever, you get 2 ways of interpreting that area, one of which is obviously 2, and the other one is my infinite sum. This is why we call geometric sequences geometric, because they can be thought of as coming from geometry, like this. And so the series that we're fucking around with here is called a geometric series. And the next thing I'm going to do for you is prove the general result. Questions on what we did here? Certainly, I don't want to always do this. If you hand me an infinite series, I don't want to write out the first 10 partial sums and guess at the limit. That's a shitty way to do things. You know, mathematicians hate guessing. And, you know, we got lucky here that this sequence of partial sums was converging to a really nice number that we could guess easily. But if the value of the series, if these things were getting closer and closer to like pi/7, then that would be much harder to see from the decimal. So instead, what we need is a theorem. And this theorem I'm going to prove to you. This is your first major result on on infinite series. It's our theorem on geometric series. Hey, Hamlet. This says if S is a series like sigma n from wherever, 0 to infinity, a times r to the n, so one constant times some other constant to the n, is a, we call this geometric series. Geometric because the thing inside here is a geometric sequence. So the series built out of a geometric sequence is called a geometric series. If this thing is a geometric series, then S converges if and only if R has absolute value strictly less than 1. And in that case, the sum of the series, the value of the series, will be A over 1 minus R. Proof. As with all series, S is the limit as capital N goes to infinity of S sub capital N, the limit of its sequence of partial sums. And here, S sub capital N is sigma n from 0 to infinity A times R to the N. So now I'm going to write out Sn. Sn, this thing, is A plus A times R plus A times R squared plus A times R cubed, out to the second to last term is A times R to the capital N minus 1. And the very last term is A times R to the capital N. I can factor out an A, and what's left is 1 plus R squared plus R cubed. The second to last term is R to the capital N minus 1, and the last term is R to the capital N. Now I'm going to do something sneaky. I'm going to multiply through here by 1 minus R. So 1 minus R times Sn is equal to 1 minus R times A times 1 plus R squared plus R cubed. Second to last term is R to the N minus 1, and the last term is R to the N. The A can come out front, and then when I distribute the 1 minus R, first I'll multiply through by 1. I'm going to open up a big bracket. When I multiply through by 1, I just get this thing again. That's 1 plus R squared plus R cubed, R to the N minus 1, and R to the N. Now I have to subtract what I get when I multiply through by R. So this minus is this minus. A here is all the way out here. And the last thing to do is distribute this R over this partial sum. So R times 1 is R. R times R is R squared. R times R squared is R cubed. In the next few terms, R all the way out here. Well, what's the last term before R to the N minus 1? It's R to the N minus 2. And when you multiply R to the N minus 2 by R, you get R to the N minus 1. When you multiply R and R to the N minus 1, you get R to the N. And when you multiply r and r to the n, you get r to the n plus 1. And now something quite magical happens. I have here an r and then minus r. I have here an r squared and then minus r squared. R cubed minus r cubed. A lot of stuff goes away. So I have a times, this 1 never gets killed. There is no 1 over here. So the 1 survives. The r and r go, r squared and r squared, r cubed and r cubed, r to the n minus 1 and r to the n minus 1. All of these go. Oh, there should be dot dot dots in here. Sorry. Yeah, all of these go except for the 1 and the r to the n plus 1. So I have 1 minus r times Sn equals a times 1 minus r to the n plus 1. Now I can divide back over by my 1 minus r and get a nice formula for Sn. Sn is a times 1 minus r to the n plus 1, all divided by 1 minus r. This is the formula for the partial sum of a geometric series.
Where'd the denominator come from?
I'm sorry, Ayushi?
The denominator, like 1 minus r.
What about it?
Where'd it come from?
So I had 1 minus r times Sn equals this.
Okay,
I divided both sides by 1 minus r to get Sn alone.
okay.
All right, if you want, I can write it down here. I had 1 minus r times Sn equals this. So then you divide both sides by 1 minus r, and you get Sn alone on the left, and you get this stuff divided by 1 minus r on the right. So now the full infinite series S, remember, is the limit as cap n goes to infinity of Sn, which is the limit as cap n goes to infinity of a times 1 minus r to the n plus 1 all over 1 minus r. And now you have to think about what r to the n plus 1 does as n goes to infinity. See, Sergio. If the absolute value of r is smaller than 1, then this piece right here, the highlight piece, r to the n plus 1, will go to 0. If the absolute value of r is 1 or larger, then this thing will go to infinity as n goes to infinity. Or it'll bounce back and forth between plus infinity and minus infinity. So if absolute r is less than 1, then the limit as n goes to infinity of r to the n plus 1 is 0 and does not exist otherwise. This is something we proved about geometric sequences last week. Therefore, if absolute value of r is less than 1, the series S, which is the limit as n goes to infinity of a times 1 minus r to the n plus 1 over 1 minus r, will go to this piece right here, will go to 0. So you get a times 1 over 1 minus r, which is a over 1 minus r, which is what we wanted to prove. In other words, geometric series converge to a over 1 minus r if the absolute value of r is less than 1, and diverge if the absolute value of r is greater than or equal to 1. And that's exactly what we wanted to show. That is the statement of the theorem. Now, again, you're not responsible for the proof, but you are responsible for knowing the theorem. You need to know what geometric series are. Their sums, sigma, some constant times some other constant to the n. And you need to know when they converge. They converge if and only if the absolute value of r is strictly less than 1. And you need to know, in the case where they converge, what they converge to. They converge to the starting term, whatever that is, divided by 1 minus r, where r is the common ratio. A quick note. This formula, a over 1 minus r, isn't perfect. The more general formula, because these series don't always start at 0, more generally, you'll converge to the starting term, like the first term in the series, whatever that is, over 1 minus the common ratio. And that's if the absolute value of r is less than 1. Otherwise, these series diverge. So we can return to the series we were playing with and made that guess about a minute ago. I could say investigate the convergence of the series s equals sigma n from 0 to infinity, 1/2 to the n. This is geometric. This series is geometric with a equal to 1 and r equal to 1/2. So the absolute value of r is the absolute value of 1/2 is 1/2 is less than 1. So the series converges. And its value or sum is, well, the starting term here, what's the first term? It's 1, because the series is 1 plus 1/2 plus 1/4 and so on. So the value here is 1 over 1 minus 1/2. That's a over 1 minus r. So that's 1 over, well, 1 minus 1/2 is 1/2. So it's 1 over 1/2, or 1 times 2 over 1, which is 2. So we guessed correct when we were working on that. There's a joke here. An infinite number of mathematicians walk into a bar. The first guy goes, "Give me a beer." The second guy goes, "Give me half a beer." The third guy goes, "Give me a quarter of a beer." The next guy goes, "Give me an eighth of a beer." And the bartender chuckles and says, "I fucking hate you guys," and pours 2 beers. Bad joke, I know. So these are geometric series. Let's look at one more example of a geometric series, and then we're going to move on. Same thing, investigate the convergence of the series let's say s equals 2 minus 2/3 plus 2/9 minus 2 over 27 plus 2 over 81 minus, and so on. So this time the series hasn't been given to me in sigma notation. So your first task is to write it in sigma notation. if you look for patterns here, you'll notice that to go from 2 to negative 2/3, you multiply by negative 1/3. To go from negative 2/3 to positive 2/9, you multiply by negative 1/3. To go from 2/9 to negative 2/27, you multiply by negative 1/3. And again, multiply by negative 1/3. So the sequence AN is geometric. It's 2 times negative 1/3 to the n. So the series S is the sum from n equals somewhere. Let's see, in this case, this works if n starts at 0 to infinity of 2 times negative 1/3 to the n. And the thing we just did here is an important skill. Going from a series that's written out in the ... notation, in these ellipses, to the sigma notation. Now this won't be hard if you've practiced this in the sequence homework, right? Where I give you the first few terms of a sequence and you write down the formula for AN. It's the same thing, just here you need to put the AN inside of a capital sigma because we're not listing the terms, we're adding them all up. And now that we have this formula, now that I have this thing in sigma notation, I can say this is a geometric series. Because it definitely fits that form, sigma A times R to the n. So here A, the constant is 2, and R is negative 1/3. So the absolute value of R is the absolute value of negative 1/3 is 1/3, which is less than 1, which means the series converges. And has sum S equals, well, what's the starting term here? It's 2 divided by 1 minus the common ratio, that's 1 minus negative 1/3. So that's 2 over 1 plus 1/3. 1 plus 1/3 is 4/3, so that's 2 over 4/3, or 2 times 3/4. You can cancel the 3 and the 2 and the 3/4, and you get 3/2. So if you add up all the terms of this sum, you'll get 3 over 2, 1.5. And you can test this out doing the same sort of thing that we did on that very first example, where you just say, start writing out the SNs. S0 is 2, S1 is 2 minus 2/3, S2 is 2 minus 2/3 plus 2/9, S3 is 2 minus 2/3 plus 2/9 minus 2/27. And if you compute each of those numbers, they will get closer and closer and closer to 1.5, or 3/2. So geometric series are not hard to work with, but you do need to learn how to recognize them, and you need to remember this result, that it's the absolute value of R which tells you what's going on, not R itself. That's so important, the absolute values, people forget that. And then of course the formula, if the series converges, that is, if the absolute value of R is less than 1, then the value of the series is always the starting term, whatever that is, i.e. the first thing you get when you write it out in this long form, divided by 1 minus the common ratio. Okay. So we do have to keep moving. I know we're going quick today. I'll ask you to do your best to keep up. If you fall behind in the note-taking process, just leave some space in your notes. Come back and watch the video after it's up. It will be up a little later today. But I've got a couple more things I need to show you guys before I can let you go. I told you I'd be giving you a few convergence tests today. This is your first real official convergence test, and it's not actually a convergence test, it's kind of a divergence test. It's called the test for divergence, and it says simply if the limit as n goes to infinity of an is not 0, then the series S equals sigma an, and it could be summed from anywhere, 0, 1, 5, up to infinity, diverges. And then if lim n to infinity an is 0, the test is inconclusive. And you need to remember both of these. I'm writing it this way, which is a little bit different than how your textbook writes it because people fuck this up so much. Most of the time, you just learn if the limit of the an's is not 0, then the series diverges. And people misinterpret that all the time as saying if the limit of the an's is 0, then the series converges. That's not true. It's not true at all. There are lots of series where the limit of the an's is 0, but the series still diverges. What this does is it provides you a quick way to check if a series even has a chance of converging. I'll sketch for you a quick proof. Suppose the limit as n goes to infinity of an is equal to L, where L is not 0. Then for big values of n, an is very, very close to L. All right, that's what it means to say that the limit of the sequence an is L. It means that as n gets bigger and bigger and bigger, the an's get closer and closer and closer to L, and they stay close to L.
Does that say suppose?
Mm-hmm.
Okay.
What's the thing that people mess up for that theorem?
This theorem, they think that if the limit is 0, then the series converges. That's not true. So if the limit of the an's is not 0, then the series diverges. That is true. But if the limit of the an's is 0, the test is inconclusive. So the thing people mess up here is they say lim n to infinity an equals 0 implies that the series converges. This is not true. So I wouldn't even write the pink. All right, just write the black. If the limit of the an's is not 0, then the series diverges. If the limit of the an's is 0, the test is inconclusive. So here I'm going to prove that if the limit is not 0, then the series diverges. If the limit of the an's is equal to some non-zero number L, then for big values of n, an is close to L. That's what it means for the an's to have limit L. So the series S looks like A1 plus A2 plus A3 plus A4 all the way out. And then you've got some big values like A100 plus A101 plus A102 plus, and so on. These first few terms, I don't really give a shit what they are. But all these late terms, because n is large here, A100 should be close to L. A101 should be close to L. A102 should be close to L. A103 should be close to L. there's infinitely many copies of something here that is very, very close to L. I should say this is very, very close to, not exactly equal to. And this stuff here, I don't care what it is, but it's definitely finite because there's only finitely many terms. So you end up with something finite plus L times infinity. And since L is not 0, L times infinity is definitely infinity. You add something finite to something infinite, you get something infinite.
Does that say, what does it say, infinitely many?
Copies.
Okay, thank you.
Yeah, infinitely many copies. So L plus L plus L plus L infinitely many times. So if the limits of the AN is equal to some non-zero number, then the series S has to have some infinity. In other words, S diverges. And that's it. That's the proof of the test for divergence. It says if the limit of the ANs is not 0, then the series has to diverge. There's a bunch of ways you can use this. One example here, we could investigate the convergence of the series sigma n from 1 to infinity n squared minus 1 over n squared plus 1. So what does this look like? Well, that's 0 plus 2 squared minus 1 is 1 over 2 squared plus 1 is 5 plus 3 squared minus 1 is 8. Or sorry, 2 squared minus 1 is 4 minus 1 is 3, sorry. And then the next term would be 8 over 10, and then 15 over 17, and so on. So I want to know, does this series converge or diverge? And I can use the test for divergence here. So the test for divergence says if the limit as n goes to infinity of the ANs is not 0, then the series diverges. Well, here the limit as n goes to infinity of the ANs is the limit as n goes to infinity of n squared minus 1 over n squared plus 1. And if you divide top and bottom by n squared here, you get lim n to infinity 1 minus 1 over n squared divided by 1 plus 1 over n squared. The 1 over n squareds go to 0, so that's 1 over 1, which is 1. And 1 is definitely not 0. So the series sigma n from 1 to infinity, n squared minus 1 over n squared plus 1 diverges by the test for divergence, which we'll abbreviate here as TFD. Easy as pie, right? Life couldn't get any easier.
I had a question about the renormalization trick. When you do it, does it have to be with the highest power, like the highest power in the denominator or in the whole thing?
You can try using the highest power in the denominator, and that will sometimes give you the result, but I recommend dividing top and bottom by the highest power anywhere.
Okay, thank you.
So I do have one more warning associated with this thing. The series sigma n from wherever to infinity of an is not the same as the limit n to infinity an. Okay, every semester on exam 2, I see at least one person say that these are the same. They write this equals this, and that's just not true. They're totally different things. This is like a horizontal asymptote. This is like a type 1 improper integral. Those are not the same. So why would a series be the same as the limit of its terms? It just doesn't make sense. Please don't write this. These things can be related to each other using the test for divergence. If this limit isn't 0, then this series diverges. That much is true, but only that much is true. All right. We still have one more big thing for me to show you. And that one remaining big thing is what's called telescoping series. So far today, we've learned what infinite series are and what it means for them to converge. We've learned what geometric series are. They're series built out of geometric sequences. And we learned that they converge only when the absolute value of R is less than 1. And we've also learned this test for divergence. So in your special convergence section in your notebook, you should add from today 2 things: the test for divergence, which we just talked about, and the theorem on geometric sequences. This last thing that I'm about to show you, unfortunately, can't be written really succinctly in the same sort of way as the geometric series result, but it is nevertheless important. These are called telescoping series. A series whose partial sums have a lot of cancellation are called telescoping. So like those big pirate telescopes that you see in cartoons where dudes like pull it out and they're like scanning around and they see an island like land ho, and then they foot dump, smash the telescope down into a little space. That foot dump, that process is called telescoping. And telescoping series are series where there's so much cancellation from one term to the next that the whole infinite series goes foot dump into just a few terms. To say the whole series does that is a little misleading because really we should be thinking about partial sums. So this is how I define a telescoping series.
Professor, can you read that sentence? It's kind of blurry. It's hard to tell.
Sorry, yeah, the camera on this fucking thing doesn't focus and it really doesn't help that my handwriting sucks. A series whose partial sums have a lot of cancellation are called telescoping.
Thank you.
All right, you're welcome. So the best way to learn about these things is through examples. Let's investigate the convergence of the series S equals sigma n from 1 to infinity 1 over n squared plus n. Definitely not geometric, right? The things here are not like some constant to the n. No way. If you try to run the test for divergence, the lim as n goes to infinity of an is the lim as n goes to infinity of 1 over n squared plus n. You don't need to renormalize here because the top isn't going to infinity, just the bottom is. This is 1 over infinity, which is definitely 0. And what does that tell us? What does the test for divergence tell us in the case where the limit of the an's is 0?
That it converges. Diverges, sorry.
Nah, go back and read it.
Inconclusive, sorry.
Yeah, not a goddamn thing, unfortunately. So this is inconclusive. Sorry to those of you who answered in the chat there. I know I'm sure a bunch of you were screaming it. Yeah, good, okay, good. So this ain't gonna work. Now, if it's not geometric and TFD doesn't work, I don't have any other tricks at this point. We're just starting to do this. The only other thing I have is the definition of an infinite series. And in mathematics, as in elsewhere, if you don't have anything else to work with, you gotta start with the definition. So S is the sum from 1 to infinity, 1 over n squared plus n. That is the limit as capital N goes to infinity, sigma n from 1 to capital N, 1 over n squared plus n. You write it as a limit of the sequence of partial sums. Now, you can factor that denominator. And I told you back when you were first learning partial fractions that the real reason we did this isn't for integrals, but for something else. Congratulations, you have made it to the something else. We're going to do some PFD on this. And that's going to allow me to write that as a difference of two things. And then when I write out this partial sum, I'm going to get a lot of cancellation. So I need to run PFD. And most of the time with telescoping series, you will run PFD. So I say 1 over n times n plus 1 is equal to a over n plus b over n plus 1. And then I cross multiply to get rid of denominators. I get 1 equals a times n plus 1 plus b times n. And if you evaluate that at n equals 0, you get 1 equals a times 1, or a equals 1. And if you evaluate that at n equals -1, you get 1 equals b times -1, which means b is -1. So S, so here's all my PFD. So S is the limit as capital N goes to infinity of sigma n from 1 to capital N, 1 over n times n plus 1, which according to my PFD work is the same as 1 over n minus 1 over n plus 1. And now I write out this sum. This is lim n to infinity, open up a big bracket. I'm going to write out this finite sum. It has capital N terms. When little n is equal to 1, the first term is 1 over 1 minus 1 over 2, plus. When little n is equal to 2, the second term is 1/2 minus 1/3, plus. When little n is equal to 3, I have 1/3 minus 1/4, plus blah, blah, blah. When little n is equal to capital N minus 2, the second to last term, I have 1 over cap n minus 2 minus 1 over cap n minus 1. Oops, shit. Minus 1 over cap n minus 1. Plus, when little n is equal to cap n minus 1, I have 1 over cap n minus 1 minus 1 over cap n plus, and then my very last term here, when little n is equal to capital N, I have 1 over cap n minus 1 over cap n plus 1. Okay. Now you look for cancellation. This guy cancels with this guy. This guy cancels with this guy. This 1/4 would cancel with the first term inside these dot, dot, dots. Right? What's the pattern? The cancellation pattern is that the negative piece of a given term cancels with the positive piece of the next term. The negative 1/3 in the n equals 2 term cancels with the positive 1/3 in the n equals 3 term. So the negative 1/4 in the n equals 3 term would cancel with the positive 1/4 in the n equals 4 term. Looking at the tail, there's a similar pattern. The 1 over n minus 1s eat each other up. This 1 over n and this 1 over n eat each other up. And the 1 over n minus 2 term here would be canceled by the negative 1 over n minus 2 from the previous term that's hiding in the dot, dot, dots. So all of the stuff in the curly or in the square brackets there simplifies to 1 over 1 minus 1 over n plus 1.
Where did the 1/4 cancel?
The 1/4, so what's the next term inside the dot dots?
Okay, that makes
1/4 minus 1/5. It's tough to see. This stuff takes practice. And you need to be able to spot the cancellation pattern to say for sure who lives and who dies. But even though it's not written, there's a positive 1/4 in the dot, dot, dots. That's the next thing. So that positive 1/4 would eat up this negative 1/4. And then everybody else in the dot, dot, dots eats up each other, except for the very last term, which is minus 1 over n minus 2. And he eats up this guy. Then these guys eat up each other, and this guy survives. So the very first term and the very last term survive. That's that telescope, right? The very first term and the very last term survive. Everybody else goes foot-a-dump. Now as capital N goes to infinity, 1 over capital N plus 1 goes to 0, so this limit is 1. So we learned two things. Thus, the series S converges, and that's by the definition because the limit as capital N goes to infinity of Sn exists and is equal to 1 and has value or sum S equals 1. So that is it. And that's today's lesson. So I know that's a lot. We've managed to come in just in time. So let me tell you just a few things and try to help you gain a little bit more intuition. First, these telescoping series, you don't always do PFD, but you usually do. So if you're handed a series where you could do PFD, you should do it and see if the series telescopes. There's only two types of series in all of series land where we can figure out the sum. Those are geometric series and telescoping series. So if a problem asks you to find the sum, you know it's got to be one of those. So you got to get good at spotting geometric series and spotting telescoping series. Everything else we need other tools for. The sequence Sn is not the same as the sequence An. Remember, S1 is A1, but S2 is A1 plus A2. S3 is A1 plus A2 plus A3, and so on. S capital N is A1 plus A2 plus A3 all the way out to AN. People do tend to get SN and AN confused. And remember that the full infinite series is the limit as capital N goes to infinity of the finite series. And that finite series is the thing we call Sn, right? So this is the definition of an infinite series. And it's very similar to the definition of a type 1 improper integral. I want to show you, and this is where we'll pick it up on Wednesday, how exactly you can think of these infinite series as the integral of a sequence. So maybe here's 1, 2, 3, 4, 5, 6, 7, 8. And maybe up here, here's A1. And maybe here's A2. Here's A3, A4, A5, A6, A7, and so on. If I draw in some rectangles, each one of these rectangles has width 1. So I started with the graph of the sequence AN. So the height of this dot is the value of A1. And since the width of this rectangle is 1, its area is A1. Similarly, the areas of all these just come from their height. So you can think of the infinite series, sigma from 1 to infinity of AN, as the sum of the areas of these rectangles. And thinking about it like that, you should start seeing a connection to integration. The sum of a sequence, a series like this, which is the sum of a sequence, is very similar to the integral of a function. If the sequence is the function, then the sum is the integral. And what we're doing when we mess around with these infinite series is we're doing something very similar to trying to integrate a function like this from 1 all the way out to infinity. So this is very, very similar to the idea of integrating from 1 to infinity f of x dx. Not just similar in terms of notation, but similar in terms of what it's computing. And this is what we're going to be talking about on Wednesdays, the precise relationship between the area under the pink and the area of the rectangles. This is called the integral test. And that is where we're going to pick it up on Wednesday. Any last minute questions for me before I let you guys go today? I know this was a lot.
What do you think the next test will be?
Probably Monday after next. We did PFD in the last problem because we could, and because doing it made things nice. Because when I run PFD on this, it becomes this. And when I write this out, there's lots of cancellation. So this is something that comes from a priori knowledge. I knew that if I did PFD on this, the result would be something that has a lot of cancellation. And what you should learn from that is that when you see something like this, you should try PFD, because then you might get something that looks like this, and you might be able to cancel the terms like that. So this was to give an example of what are called telescoping series. My last bit of parting wisdom here to you is read the textbook. Read section 11.2. Everything that we're going to do for the next 2 weeks, and in truth, the next 2 weeks after exam 2 as well, is built around section 11.2. So please read section 11.2 in the textbook. If you don't have a copy of the textbook, contact me. I will get you one you can read. Read section 11.2. It has examples that we didn't have time to talk about. It will give you the ability to see the theorems written in different words than I use. It'll have lots of pictures and things that may help you. And there's nothing quite like reading shit for yourself. So please read section 11.2. All right. There is going to be a new homework. It's going to cover sections 11.2, 11.3, and 11.4. I've pre-recorded the lecture videos for Wednesday and Friday because I will be out of town, and they are already up on my YouTube channel, but I don't recommend watching them right away. I recommend starting on the first few homework problems, going through, read the textbook. Go through your notes while you read the textbook, fill in any little bits you want to fill in, work some examples. Then start the first few homework problems. And then if you want to, go ahead and watch those other lecture videos early, but you can watch the Wednesday video on Wednesday and the Friday video on Friday. That would be my recommendation. In between, work some homework problems, try to understand things. Even though I will be out of town from tomorrow through Saturday, tomorrow through next Sunday, I will have my laptop, I will have my webcam, and we will still be doing office hours as well as I can. And I'll definitely be answering emails, Canvas messages, and all that stuff. So all the normal communication stuff is still there. Treat it like a normal week. The only difference is the lectures are pre-recorded. Okay, I got to get running. I got some other things to do. I hope you guys have a lovely rest of your day. If you want to talk about anything, I do have a normal office hours, and you can reach out to me through Canvas or email, all of that stuff. So yeah, that's it. Work hard. All right. Remember, this section is foundational, not just for all the stuff between here and exam 2, but also for power series and a bunch of the shit that's on exam 3. This section is so important. This section is the reason people fuck up in Calc 2. Don't fuck up. Read the book. Read the book. Work hard this week. You'll be all right. Okay. And I'm here for you if you get in trouble. Okay. Take care.